All right, class. So far we've gone over a number of different reactions of aromatic rings, and let's look at this reaction here and see uh, why this reaction doesn't fit into one of the reactions we've covered involving aromatic rings. So when I look at this molecule here, a couple of things I'm looking for. So I see an aromatic ring and I see some reagents, and you might be thinking, okay, this is an electrophilic aromatic substitution. Unfortunately, though, if I look over here, this is electrophilic, but this isn't electrophilic. None of the electrophilic aromatic substitution reactions that we've gone over have involved a nucleophile as one of the reagents. So this is telling you when you see something that's nucleophilic. So remember, when you see sodium hydroxide, we want to think of this as we want to really think of this as Na plus and OH minus, right? And this is nucleophilic. We haven't really ever seen a nucleophile being used as a reagent, or we haven't seen a nucleophile being used as a reagent in an electrophilic aromatic substitution. And in fact, what this is not an electrophilic aromatic substitution. This is what we call a nucleophilic aromatic substitution. This is a reaction where the benzene ring is attacked by a nucleophile. And the product you get from this is where the OH minus, which is the nucleophile here, so the OH minus here is going to add to this carbon here. And what it looks like it does is it looks kind of like an SN2 reaction. We're going to go over this. It's not an SN2 reaction, but it looks like it did some kind of little SN2 reactionist to get to that product, right? So this is what we call a nucleophilic aromatic substitution, because the OH here, which is a nucleophile, is substituting for something on the aromatic ring. So nucleophilic aromatic substitution. And remember, when you do when you're doing a nucleophilic substitution, just like in the SN1 or SN2 reaction, you need a leaving group, and we know the halogens are good leaving groups based on the alkyl halide chapter. So what's happening here? Well, what's happening here is that when you have the OH minus, that OH minus is nucleophilic enough. Now, again, what we've usually gone over is the fact that this aromatic ring is nucleophilic, but I have this strong electron withdrawing group on there. I also have this thing which is also electron withdrawing. So that makes this ring pretty deactivated. And it actually shifts the reactivity of this molecule, of the benzene ring, from being nucleophilic to electrophilic. So I do a nucleophilic attack on the carbon with the leaving group. And notice I make something called the Meisenheimer complex. That's a really fancy, that's based on someone's name. What this is it's a resonance stabilized carbanion. So look, when the and this is pretty cool. This is why these ideas of resonance and inductive effects, but resonance stabilization, this is why resonance stabilization is so interesting and so cool. It helps explain why this weird reactivity even takes place. This anion is relatively stabilized by this strong electron withdrawing group, right? And make the anion here. This anion is resonance stabilized. The nitro group is one of the strongest deactivators, both for its electron withdrawing ability inductively, but also for its resonance electron withdrawing ability. Right? So when I have the anion here, we move the anion around the ring, and you see there's this extra resonance structure where the electrons get pushed up toward the nitro group. That's 4 resonance structures. Anytime you can draw 3 or 4 or 5 resonance structures, whatever carbocation or carb anion you make is really stable. All right. So what happens here is you make this resonance stabilized anion, and then we lose the leaving group. So the leaving group leaves, and then you remake the aromatic ring. And the driving force to go from here to here, right, is the fact that the molecule, even though this anion is resonance stabilized and relatively stable, it doesn't want to stay the anion. It wants to go back to being an aromatic ring, right? Like even though technically, so if you kind of think about this molecule over here, right, it's kind of and then these molecules are still kind of they're not sad, they're not feeling totally great, right? But then once you make this molecule is aromatic, and I'm in a better place, right? So we're making something more stable here. So in order to do these electrophilic aromatic substitutions, so one thing to keep in mind is that because these are under acidic conditions, so if you go back to this, you see that there's this second step of acid. Well, the reason why you have to have that second step of acid is because the first step is when you do this, you don't actually make this out of that first step. You make the phenoxide anion. So you need that acid workup in order to protonate to go from here to here. And three things you need in order to do a nucleophilic aromatic substitution. The benzene ring must have a must have a strong electron withdrawing group, a nitrile. So the things that are the strong. These are the things that we call the these. So the benzene ring must have a strong, or what we have, or what the one of the ways in that list are. These must have, oh, I can't spell, sorry, must have a strong deactivator on it, okay? And then coupled with the strong deactivator, the ring must have a good leaving group, maybe a halide, right, or tosylate, something that's a good leaving group. But the leaving group has to be ortho or para to the electron withdrawing group. So what that means is I can do nucleophilic aromatic substitutions, right? If I have a strong electron withdrawing group here and the halide here, or I can do a nucleophilic aromatic substitution if I have an electron withdrawing group and the halide there. And what this is where the halide is, that's going to dictate where you add the nucleophile. So if I do a nucleophilic aromatic substitution here, I'm going to be replacing whatever is here. If I do a nucleophilic aromatic substitution on this molecule, I'm going to be replacing whatever is here. And to keep in mind, I can increase the rate of this nucleophilic aromatic substitution as I add more electron withdrawing groups onto the molecule. So for example, this reaction here is not set up to do a nucleophilic aromatic substitution. So let's go over the ways I know that this is a nucleophilic aromatic substitution. I have an aromatic ring, right? So I see my aromatic ring. I go over to here. I see sodium hydroxide. I see something that's nucleophilic / basic. So we're not doing an electrophilic aromatic substitution. So that if I'm not doing a nucleophilic aromatic substitution, I might be doing an electrophilic. So I go back here and I go, okay, I have my strong electron withdrawing group. I have a leaving group, but this leaving group is not ortho or para. It's meta. The Meisen hypercomplex is not stabilized. You don't get that extra resonance structure when the leaving group is meta. And again, you don't see the reaction when you do it without the nitro group. You need that electron withdrawing group to get this reaction to work. Now, if I heat the living bejesus out of this molecule, then all of a sudden I can get this reaction to go. But the moment you start heating anything to 350 degrees, like that's not cool. Molecules generally don't like to be heated to 350 degrees. All right, so I hope that that was like a very new reaction we added. So take some time, try to process that. Let me know if you have any questions, and I'll talk to you later. Thanks, and have a great day.